for today's lab is we are going to test whether the law of conservation of momentum is valid in collisions. And we have two different kinds of collisions, okay? One involving the iOLab and one involving a little video. And we're going to test whether our understanding of conservation of momentum is valid, okay? So in the first part of the lab, can I still see my iOLab here? Yeah, let's reset the iOLab. Reset. Let's bring up the force and the wheel and just display, oops, my battery's dying in the iOLab, so I have to turn it on every few minutes. Okay, so what we're going to do is we're going to take the iOLab, right? And we're going to collide it with the short spring, okay, the small spring, okay? We're going to have it undergo a collision with a brick wall. Okay, it's not a brick wall, it's my phone, but you get the idea. Collision with a brick wall, right? And if our understanding of conservation of momentum is valid, then momentum should be conserved in that collision, right? Or, given our understanding of the force impulse theory, it should be true, right, that the impulse provided by the wall on the cart, which is going to be the change in momentum of the cart, the impulse supplied by the wall to the cart should be the change. Oops, I'm accidentally dialing someone. I should use something else as a brick wall. The impulse momentum theory says that the impulse is the change in momentum, and the impulse is the area under the force versus time graph, right? So let's, as I said, bring up a graph of force, right? Force measured by the force sensor, and velocity of the cart. Let's start taking some data. Uh-oh. Oh, wait, I'm on the wrong computer. Take some data. To turn this back on. I hope my battery's not dead. Okay, oh no. Sometimes I get these weird Bluetooth interactions. Let me try it on, let's see. Let me try it this way. Oh, well, come on. All right, I may have to get some new batteries. Let's try this. Okay. So I'm going to take my iOLab. I'm going to collide it with the wall. Boom. Okay, stop. Here's my collision. Okay. So what's going on? What is this depicting? Someone describe what's going on here with these two graphs physically. Sorry, you're all distorted. I can't make out what you're saying. What's going on here? We have a force, okay? We have a force, first of all, that's negative, okay? Let's make the force positive by clicking on reverse y-axis, okay? We have a velocity that's negative and then becomes positive. Let's also reverse the velocity graph. So we have a velocity that's positive and then goes to negative, okay? What's happening here? The wall is exerting a force on the cart, right? And therefore changing its momentum, right? The momentum goes from a positive value here to a negative value, right? Once we multiply by the mass of the cart. So there's a big change in momentum here, right? Positive MV to negative MV. Okay, so final minus initial is going to be negative MV minus MV, which is negative 2 MV. Okay, and if our theory of conservation of momentum is true, then the difference in momentum between the moment when it hit the wall and the moment when it left the wall, the change in momentum should be what? It should be the area under this graph, force versus time, right? The area under this graph is called the impulse. So if I click on my data analysis tool and select the part of the graph where the force was non-zero, okay, the area under that graph is the letter A here, right? 0.070 Newton seconds. And that should be, looks like it's a little, not quite aligned. That's interesting. That area should be the difference in the momentum, the change in momentum of the cart from this moment to this moment. Now, I'm not sure why they're not lined up here. That's interesting, right? Because the velocity here should start decreasing the minute the spring contacts the wall. Let's take some more data, see if this is, we can get some better data here. Oh, come on. Looks like these batteries are dead as well. Dang it. All right. Well, we'll have to go back to that original data here. What the heck? Let me get rid of this, get rid of this, get rid of this, get rid of this. Okay, here's our data. And again, the area under the force versus time graph, which is called the impulse, should be the change in momentum from the point where it first hit the wall to the point where it left the wall, rebounding backwards. So your job is to calculate the momentum just before it hit the wall, calculate the momentum just after it left the wall, find the change in momentum, and compare that value to the area under the force versus time graph. Okay? Now you're going to have to estimate. Now, of course, I should zero my force sensor, so I'm going to select this and click re-zero sensor. There we go. You're going to have to estimate where to measure that area to calculate the impulse. Okay? And you're going to have to try to zoom in here and find the point where the cart first, the spring first touched the wall, which looks like it's about here. And the point where the spring then left contact with the wall, which looks like it's right about there. Okay? And we can then find the value here. So it looks like V initial is about, well, if I switch the direction here, V initial is 0.319 meters per second. V final is negative 0.263 meters per second. So let's see if the change in momentum is equal to the area under this curve, minus 0.089 Newton seconds. Okay? Okay, does that make sense, what you're seeing on the graph there? Yes? No? A little bit?
Yes, that makes sense.
Thank you. Thank you. Who's that? Brenna? Thank you very much. Ugh. Okay. Let's see if the impulse momentum theorem is true. Change in momentum is area under force versus time, aka impulse. Okay, that's the first part. Then the second part of the lab is to, now I'm going to have to go over to this computer because that one doesn't have tracker on it. You guys see tracker here now? Yeah. Okay, the second part of the lab exercise is to actually calculate the change in momentum in a collision of two objects. Okay, and to do that, we're going to use tracker. Hopefully you all remember how to use tracker, right? So here's tracker, this software, and you're going to open this file that I uploaded onto Canvas. It's called collision.mp4. Okay. Here's the video. It's a very exciting video. Let's watch it. Oh, cool. There's a collision between two cars on this very track right here. Okay. And we are going to see if momentum is conserved in this collision. Now, I gave you the masses of these two carts in the lab exercise. One is like 400 something grams and the other is maybe 900 something grams. Anyway, I gave you the masses of the cart because you can't measure those. So you're going to calculate the initial and final momenta of the system. Okay, the second cart here is at rest, and the first cart comes in and collides with it. And then they rebound. Okay, the first cart rebounds backwards, the second cart rebounds forwards. Okay, so just to remind you how to use tracker, right? We first set up a coordinate system. You click on the little coordinate system icon. That gives you a purple coordinate system. You're going to drag the coordinate system so the origin is right at the point where the two carts collide, right about there. You're going to make sure the x-axis is aligned with the track, something like that. I'll let you play with it. So our x-axis is now along the track, so this is a one-dimensional collision. There's not going to be any motion in the y direction, a one-dimensional collision only in the x direction. Okay, and then if you remember, you have to create a scale. So you click on the little scale icon, go down to new and click calibration stick. And I conveniently put a ruler here in the picture. So you hold down shift, click on one end of the ruler, hold down shift, click on the other end of the ruler, and then enter the length of that object, which is about 0.3 meters. You can find the exact length of a 12-inch ruler by converting units, okay? So now we have a coordinate system, we have a scale, and now we just have to track our objects. So if you remember, you click on, I can't see here, oh, because this thing is in the way. You click on create, click on point mass, and now you hold down the shift key and mark the position of your mass. So I'm going to first mark the position of cart A, the one that comes in from the left. So I hold down shift and I pick a point on the cart and then consistently click on that point over and over again as this goes frame by frame. I'm doing this very crudely. You're going to do a much better job, of course. Here comes the cart. And here comes the collision. And here's the cart after the collision. Again, I'm doing this very crudely just to show you. Okay, you can do more points than that. But look at that. There's the graph of the motion of that cart. Here's the x position of the cart as a function of time. And just as expected, what does it do? What is this graph showing this cart doing? This is a very simple x versus time graph. What is it doing? Describe physically, somebody. What's this cart doing? What does this graph show?
Yeah, iOLab changed direction. Well, the object changed direction.
Yeah, it's not an iOLab, but it shows a cart moving at a constant positive velocity, i.e. a straight line with a positive slope, right? Constant positive velocity, then there's a collision, and then after the collision, the object moves at a constant negative velocity and a lower speed than when it came in, right? Because the slope over here is less than the slope over here. The magnitude of the slope, sorry. The magnitude of the slope here is greater than the magnitude of the slope here. So this is an object that came in from the left moving quickly and then went off to the left moving slowly. Okay, and now we can click create another point mass. Let's go back to the beginning. And this is mass B, and mass B will be at the other cart. So I'm going to hold down shift, and this is easy because cart B is not even moving at all for a while. And then after the, whoops, click too fast. And then after the collision, of course, we always want to click on the same point on each cart, right? Because we're tracking these objects as if they are point masses. Okay, I'm doing this crudely. You're going to do a better job. But there's my graph of mass B. And what does this describe physically? Well, and before the collision, we have a line with constant zero slope. That means the cart B is not moving. After the collision, we have a straight line with constant positive slope. In other words, the cart is moving off to the right at a constant speed. Okay? And now, all you have to do is measure the average values of the initial and final velocities for both carts. So if you remember how to do that, you right-click on this graph, go down to Analyze. There's a close-up view of the graph for cart B. Now, we don't even really need to, but we can measure the average velocity before the impact, and clearly that's 0. Okay? Now, let's change this to velocity. Change this to velocity in the x direction, sorry. And let's go to Analyze, and clearly the velocity is 0. Before the collision, and then after the collision, if I select all these points, I get an average velocity. The middle column, see where it says Vx? The middle column is measuring the velocity. And if I click on Analyze and Statistics, I get a mean value of 2.773. Oops, I may have to expand that to see the decimal point, yeah. So the average value of the velocity of cart B after the collision is 2.773 e minus 1, or 0.2773 meters per second. Okay? And then I can go back to mass A, change its graph from position to velocity, right-click, go to Analyze, and now measure, click on Analyze, Statistics, select the points before the collision, and it looks like I got a mean velocity of 0.4635 meters per second. And then a mean velocity, if they select these points after the collision, of negative 0.1545 meters per second. And now I have all the information I need to calculate the initial and final momenta of the system. And let's see if the momentum is conserved in this collision. Okay. Does everyone remember how to use Tracker? Vaguely? Hopefully you still have it on your computer somewhere. I know it's Friday. Somebody besides Brenna has to respond. Come on. Brenna and Ryan are the only two who are talking today.
Yeah, I remember.
Aiden, thank you. Right on. Okay. So that's the plan. Also, at the end of the lab, as you read it last night, you noticed that I want you to calculate the coefficient of restitution of this impact. Okay, the coefficient of restitution. And remember, the coefficient of restitution is a number between 0 and 1 that indicates how close this collision is to elastic. If the coefficient of restitution is 0, it's perfectly inelastic. That's nowhere near elastic. That's as far from elastic as you can get. And if the COR is 1, that means the collision is perfectly elastic. No kinetic energy lost to friction, deformation, heat, sound. Okay? So think carefully when you calculate that COR about the result. Does it make sense? Think about what you expect it to be and see if your expectations are fulfilled. Okay? Okay. So that is the lab. Let's make sure we understand it before I let you, or the lab exercise. I shouldn't call it a lab, it's a lab exercise. You're just going to fill in the blanks, right? You're not going to write an entire abstract lab report. You're just going to fill in the blanks. Okay? By the way, here's a ping pong ball. I'm bouncing it off the table. How do you know that collision is not elastic? Anybody?
It loses height on the second bounce.
Good point. It does not rebound to the same height I dropped it from. That's one clue. But suppose I dropped it from up here where you couldn't see how high I dropped it from. Oh, I gotta drop it straight too. Okay, now I've lost it. But how else could you tell from that bouncing ball? Very good. You can hear it. What does that tell you? What does that mean? The fact that you can hear it.
It's causing vibrations.
Okay, so it's causing vibrations.
Which means it's losing energy to heat.
Aha. That means some of the initial kinetic energy has been transferred into the air molecules, which bounce their way to the microphone and then into your ear. So clearly that collision with the ground could not be elastic, because if it was, there's no way any of the energy could have been transferred into the air, and you would not hear it. So the very fact that you can hear the ball bouncing means that it is not elastic. Okay? And of course, neither is any real-world collision macroscopically. But let's just see how close to elastic the collision of these two carts is. Let's see what the COR is and see if it is in the neighborhood of what you expect it to be. Okay? Okay. I think that's enough to get you started. What do you think? Any questions about it? Two parts, two different kinds of collisions. An iOLab with a fixed surface and two carts colliding in a video. I had a second video with a two-dimensional collision of some billiard balls colliding, but I decided not to make you do that. Maybe I'll put that one up for fun. Maybe I'll do that. I have a second video of a two-dimensional collision of some billiard balls. I'll upload that one on Canvas, and if you want to analyze that one on Tracker for fun, that might be a good way to practice your understanding of collisions. Okay? See if momentum is conserved in both the X and Y directions in the billiard ball collision. I think that one's called billiards.mp4 or something. I'll upload it in a few minutes. Okay. Does this make sense? Make sure you ask questions now. A lot of people just kind of, hey, and they go off and they start playing with the iOLab and the software, and then they come to me and they say, now, what are we doing? That's not the way to do things, right? Okay, any questions? Speak now or forever hold your peace. Nothing, huh? Okay, I will let you go off and work on this lab. I'm looking forward to reading your conservation of energy labs, full labs. This one, again, is not a full lab. It's just a lab exercise. You just have to fill in the blanks in the PDF and then upload the result. Okay. Monday, we'll have our usual quiz. We're going to tie up a few tiny loose ends in conservation of momentum and then completely change our thinking into a whole new kind of motion, rotational motion, which is going to lead to the last of the three great conservation laws in mechanics: conservation of angular momentum. So conservation of energy, conservation of momentum, now conservation of angular momentum. And then we will be done with the great three conservation laws. And there'll be more coming next semester. Okay. No other questions? Man, you guys are quiet. Okay, if there aren't, have a good weekend. We'll pick it up on Monday, quiz and on to more stuff.